Hi everyone. I'm just going to blaze on through to the next lecture because why not? Okay, we're going to look at visualization design rules now. And this normally would be lecture 2 for my visualization course, but I needed to cover sort of back end stuff first. And then, why not talk about perceptual rules first before we got into this? This lecture set will be useful for when we're doing the Dear Data series. So will perception, like Gestalt principles, but this is for when we're doing homework 5 and 6. A lot of this will be based off of how we design things based off of many of these rules. And this is going to be a bit of a Tufte fest after a little bit. So previously, we looked at cognition, perception, data seeking, data cleaning, statistics, and so many other things. We've covered a large breadth of stuff so far with this class. I'm hoping that at least the plan is to circle back with all the things we've done, like data seeking or information seeking, we probably should say instead. It's not data we're seeking, it's information. Data cleaning and statistics, how all of this fits together, at least for visualization, but for the visualization also dictates or sort of implies how it gets used in other domains as well. So when we're talking about a visualization, we're talking a static or interactive, depending on how you want to view things, visual representation of abstract or spatial data to reinforce human cognition. Okay. To reinforce human cognition is the big part of it. It allows people, the idea of the field itself is that the visual representation helps you recognize and sort of process large amounts of information. It is the foundational thing. It's helping humans deal with the sheer crazy amount of information that we have. And although you say, hey, let a computer do it, humans still have a pretty big advantage for a lot of things in terms of higher level functioning, higher level reasoning. And we're really good at visual processing of things. Extraordinarily good at this. It's like language, visual processing, and I guess higher level reasoning. And even in our high level reasoning, right? We're very, very good at this. Surprisingly good at this, at least compared to other animals. I also want to remind you, I think we briefly went over this, that we have this sort of 3-part process that is, an iterative process, but it's a dependency, as in I start off in the very rough way, and then as I iterate over and over again, I get closer and closer to the truth. I get closer and closer to a better solution, because everything is iterative normally for design. So we worry about the what is being done, why are people looking at the data, what is the data, what is the task, why are they doing it, why is it useful, and then how is the data being represented. So we normally need to know about our task, our users, and then we worry about the task, our users, our data, and then we worry about how the hell we represent it. Those first 3 things, the important things, have nothing to do with the field. Well, they have everything to do with the field. They have nothing to do with your ability to use Tableau or your ability to program a visualization. They're all about understanding the task and what people are trying to do. It involves understanding people, and that's why we have to go through all of this stuff like perception and cognition. It's why I'm not worried about it being a visualization course, because this is applicable in other parts of how we think about people. Okay. Tamara Munsner also she also proposed this nested model for how we look at visualizations. So the idea is we figure out what the domain is first. So we observe target users using existing tools. That's sort of the ideal. That would be like FAA. So American Aviator. What was the F before? Federal American Aviators? I don't know. But it's the aviation industry. They look at how people actually use what they're doing in their day-to-day lives, the current situation. Then you figure out what their task is, or what the task abstraction is. You want to figure out what the busiest day in Logan Airport is, why they're having problems, when do things get bottled up? When do things get out of hand? Then you figure out what visual encoding interaction idioms are you using? What ways are you presenting data to people? Then you might worry about your algorithms, like what's your complexity, what's your memory usage, what is it scalable, how does it scale with the number of data points that you have, that sort of thing. Then you analyze when people use these systems, you analyze the results qualitatively, like watch people use it. You measure human time in an experiment. So you figure out how people use, you make an algorithm, you see how people use it. Then you observe people using that algorithm or that system in the field, and then you measure how much it gets adopted. And once it gets adopted, then you can watch people using the system again, figure out what the data or the task abstraction is given the system, figure out this, figure out this, figure out this. When you release the iPhone, if you want to give a model that's not a visualization, you figure out what people are doing with their phones at the time. If you're Apple and you're trying to make out an iPhone, you figure out what people are using at the time. They're using horrible cell phones and they're going through heaven and hell. Or no, not heaven and hell. They're going through hell, just let's leave it at that, trying to do things like sending an email. They're looking at these little minuscule screens. They're losing pens, all that kind of stuff. You figure out what their task is. Why are they using this thing on the subway? What is their purpose? What are they trying to do with it? You figure out what you could do instead of the current version of this, the new design. You figure out how to do the new design, like if they're, touch screens for the iPhone was a big thing, right? Multi-touch on an iPhone was a crazy new thing. Solving the problem in a different way, and you have to figure out how to do the computer science, so the programming side of things. Then you see how people use the iPhone, like how they pinch to zoom. You see how fast they can click things. You see how people use it out in the real world. And then you see how many people buy an iPhone and how they adopt it. And then once you have an iPhone, then you measure what the people are doing with the iPhone and all the weird things they do with an iPhone afterwards. Okay, so we have 3 different in-class exercises, and this might go a bit long, sorry, because that was long-winded, that last explanation. So I want you to try this. Take the number. I don't know if we did this. If we've already done this, then go ahead and ignore it, but I don't think we've done this exercise yet. I want you to represent the numbers 3, 12, and 42 in as many different ways as possible. So 3, 12, and 42. Hopefully. So break into groups if you can. Groups of 4 would be better just to make it less reading for everybody. Pen and paper. Don't use anything fancy. Don't get out, stock images. No need for digital pens. Pen and paper. Just doodle crap out as fast as you can. The group with the most visualizations that can come up with ways to represent 3, 12, and 42 wins. 5 minutes max to do all of this. Put a photograph on the drive. It might be multiple photographs, or put it in a document so we can see it later. And there are several activities, so just put either clearly label your different files with your names on it, or put them all in one file. Okay. And by wins, I mean wins nothing, right? You're not gonna. Okay. So try that out. How many different ways can you represent 3, 12, and 42? The reason is because the data doesn't tell you how it's represented. The data is just a concept. You are trying to communicate that concept to others. That's what we do. And there's no necessarily correct way. There are better and worse ways. But that's what the visualization research community is looking at. How we encode data visually and the various ways we can do it to maximize cognition. So we're going to look at some do's and don'ts of visualization design. We're going to learn about Tufte's graphical integrity principles. We're going to be looking at the fuzzy gray area of interpretation of opinion on integrity, because it really matters. And you'll learn why I'm the one non-Tufte fan, it seems, on the planet. There, people are like absolute. It's like a cult. I think they have robes. Edward Tufte is a huge name in the field because he's sort of one of the first people to jump into this field. He's also from the graphic design standpoint, so he just doesn't believe in interactivity as much as other members of the field. And so I'm not as much of a Tufte fan as some other people, but he's definitely worth talking about. So here are some design rules of thumb. So these are the various books that Tufte has written. I have read all of them. They're all very, very interesting. They're a bit repetitive after a while, but still, they're very, very good for guidelines of things. Graphical integrity, his big thing is clear, detailed, and thorough labeling should be used to defeat graphical distortion and ambiguity. Write out explanations of the data on the graphic itself. Label important events in the data. Okay, that seems reasonable. People would say, well, there's too much text on there. No, you sort of need to provide some text to help make sure you compensate for distortion. So this is trying to compensate for distortion, but we still have pretty massive distortion. So so let's have a look at this. What is going on with this graphic? You might think, hey, it's one big long graphic with 3 different sets of minors. You would be wrong. What you end up getting is there are 3 different bar charts. Here, here, here. 3 different images. They are not related. But notice the Gestalt principles we have. We have this little tiny white space, so it doesn't pop that much. You can read the numbers all you want, but unless you look really closely, you're not going to notice that. So the color differences between the two and that little bit of white space is what's supposed to be, and the fact that the image changes, but the color palette doesn't change. They're all black and white. And so what you end up getting is people look at this and see it as one contiguous large graphic. But also look at the numbers. The numbers are nowhere near each other. That's $1.435102 million for net income loss. This is 7.382 for operating revenue. This is loss. They're not anywhere near each other, despite the fact they're not on the same axis, or they're not on the same scale for the axis. And this is 1 million over here, right? They are not the same things. And that's actually, but people will see it as the same thing. Clearly labeled, compensated for the distortion that you had there, but you can get rid of the distortion as well. Okay, at 11,000. Okay. There's no y-axis baseline. I really wish I wanted to talk to my wife about this. Maybe I'll go and find it. She had something very similar with her work recently, where she put 3 different bar charts on the same line. It was still vastly superior to what they had before, but since they were not aligned to one another, you could not read across the bar charts. Her boss also made a pie chart with, I think, 40 different slices of pie on it. It was not pretty. I started screaming. I didn't. Right? What you want. We need clear information, what's on each of the axes. We want to be able to clearly see what this is, and we want to avoid distortion, because look down here. This right here, 3.140, is what would normally be the 0 axis. There's all sorts of tricks you can do to lie and fool your reader, including throwing off the axis and not calling attention to it. This is actually what the difference is in terms of changing the interest rates. This, whoa, my God, the sky is falling, versus this. Right. Context makes a key thing, and normally unless you really have to call attention to it. If you don't do it, you should be starting your axes on 0, because that's what the expectation is, and people are not looking at that axis. Their attention is not on the axis to notice why the numbers are off. All right. One of Tufte's lines is double the axes, double the axes, double the. Oh, he has a term for it. Double the axes, double the mischief. Big cardinal sin is to ever put 2 different axes on the same chart, or if you're doing it, you better be very darn sure you know what's going on. Here's the membership union membership rate here. Here's the middle class share of income. They look like they're tightly correlated. Here's the union membership. Here's the middle class share of the income. Income is not decreasing remotely as much as union membership, but it looks like it's extraordinarily tightly correlated. Why? Because they changed the axes to lie to you. There it is. So let's look at some Hall of Shame things. This, I strongly recommend looking at it. You're not going to be able to shout out fame or shame to me, so let me just say, this is actually fame. Fame for me, but for a reason, not for this image. It's a Hall of Fame because the baby named Voyager was one of those things that came out of a lab, essentially, and it took off. And it's also one of the best examples of a casual visualization I've ever seen in my life, and that's my research area. So this is all baby names from 1880 onwards in the United States, the most popular 1,000 baby names, I do believe, for boys and girls. So boys are in blue, girls are in pink. And if you type in the letter A, you will get all the names that start with A. You can choose both. You can choose boys. You can choose girls. If I type AL, I will get Albert and Alice. I will not get Anna or Annie or Arthur. I'll get Alexander as well. All names that start with AL. And you'll get the pattern for how these things look. Try it out. I want you to take a pause in the video. Try out babynamewizard.com Voyager. This URL right down here. Try it out. I want to say this because, so pause for a second and I'll pick up my discussion. I'll wait. Okay. For those 4 of you that tried it out, and I hope everyone did, but I'm cynical enough to realize that most people may not have. The first thing people do, what do? They type in their own name. It's some of those things it's obvious in retrospect, but I didn't see it coming. It's one of the things I learned from my looking at casual visualizations, that it's painfully egocentric, right? And you can do all these sorts of little studies on this, that the people were studying ebbs and flows of baby names and the law names that started in the 1970s, like Latoya. They're looking at how the name David plummeted after 1960, for example, despite the fact I'm named David after the 1960s. That how Mary was a completely unpopular name. Henry is also a completely unpopular name. Henry just shot back up again recently. And everyone looks at their name, their family, and members of their family first. And some people geek out and look at patterns over time. But it's interesting in this, just as a visualization, how it's a dynamic query. As soon as I start typing letters in, everything shifts and allows me to get a sense of the data as I go. Okay, so fame, I love it. So the representation of numbers as physically measured on the surface of the graphic itself should be directly proportional to the numerical quantities measured. That is a term for data integrity, or one of the terms. This goes to lie factor, which we've already talked about before, but just to remind you. A lie factor is how off the measurement, the numerical measurement is compared to the I guess length or size on the page. So because this is 3-dimensional, the barrel in the front is way bigger than the barrel at the back, and the barrel at the back is $2.41, and this is $13.34. I guarantee you, this would be what, a bit more than 6 times this. That is way more than 6 times between 73 and 79. Hell, 78 to 79 is a difference of less than $1, and it's a huge difference in the size of the cans. It's a lie factor. So the idea is I take the size of the effect on the graphic, so hopefully I have an image of that, and a lie factor of 1, by the way, it means it's perfectly accurate. A lie factor of less than 1 is understating the value, and a lie factor of over 1 is overstating the value. This is grotesquely overstating the value. What we do, we measure the top the lines here. So the green line and the yellow line. The difference between those is 5.3 inches versus 0.6 inches. Divided by the effect, the size of effect in data. And so the image itself, the ratio for the image itself is 783%. That's how big of a difference between this line and this line. The amount of growth from there to there is 783%. The effect on the data itself is, well, let me see here. Line representing 27.5 miles per gallon versus 5.3. Okay, so 27.5 minus 5.3 divided by 5.3 minus 18. Where's 18 coming from? Oh, 18 inches long. Darn, that's a different thing. It's 5.3 inches long. It's 18 is the value here. There it is, 18, 27.5. So the difference between the two divided by 18 is a 53% increase. So 783 divided by 53 means my life factor here is 14.8, meaning it is a ridiculously high life factor. And in case you think, hey, well, it's perspective, we can see that. No, we can't. We think we can. We're really bad at it. You'll see how we misinterpret things. When you actually do measurements on it, you'll see how badly people misinterpret the data as a result. Okay, so this is a huge overstating of our life factor. That's what we're actually seeing for visual processing. Our eye is actually seeing these lines, right? So Tufte's big line is also maximize the data to ink ratio. I got a little sick of that. He constantly talks about this. So the data ink ratio is you're trying to put the absolute maximum amount of ink to show the data and nothing else. Any other bit of ink that you're using that is not showing the data or is not useful for the data should be removed. So the amount of data minus the amount of ink divided by the total amount of ink is the data ink ratio. So this over here has a despicable data to ink ratio. We have these thick lines. We have three-dimensional perspectives for no apparent reason. We have all this extra cruft around each one of these bars. Much, much better data to ink ratio. And he would actually argue getting rid of the lines unless you need the horizontal lines unless you needed them. Low data to ink ratio, and this is the high one. My word of warning is always that your data to ink ratio is not the be all and end all. Here is the genealogy of pop and rock in music, and it is an extraordinarily high data to ink ratio. It's all data. You can't use it. It's a poster you can put on your wall and look very carefully, but yeah. We also want to say that the part of the data graphical integrity is that the number of information carrying variables or dimensions depicted should never exceed the number of dimensions in the data. And what the heck does this mean? It means no unjustified 3D. If you give me unjustified 3D, I will flip out. I will rip apart your paper. It's a pet peeve of mine. I'm just stating it right for the fact. This one, I'm completely on board with it. In fact, all the research is pointing to this as well. If you use 3D and you don't need to use 3D, you can expect everyone around you that knows anything about graphic design or visualization to tear you a new one. This kind of crap, this thing here should not exist. Get rid of it. It does not look like it's coming out of the page. It doesn't look, I can almost touch the bar. No, get rid of it. It's a piece of garbage. Keep it simple. Keep it readable. Because anyone that knows about this field knows that you're trying to pull one over on us. They know that you cannot read this properly, that you're distorting the data on purpose. It's spin, essentially, right? If someone's spinning political stories on you, you just plug your ears and just sort of ignore them, right? This is trying to show the data. This is trying to look cool and like, look how fancy this. No, get rid of it. Okay. Number of dimensions of the data in this one. This is three-dimensional space, but the actual data itself has 2 dimensions. It's 3D, but you needed 2 dimensions. You need the bars. You need males and females, okay. And you need the height. Dimensions of the data is 2. Number of dimensions in the plot is 2. Big no-no. Look at these things. These are terrible, right? Horrible, even worse. And on top of all of this, hopefully I have this, I got occlusion. This bar back here is being blocked by this one. Unless you make it semi-transparent, which we still don't see properly, you're going to block what you're seeing. And I'll show you an even worse one because we've already looked at it. But occlusion is a huge thing. There's this huge lie factor because of the distortion, because the 3D is also making the perspective wrong and the measurements on this, like how you measure things, how long the bars are, wrong. It'll throw that off as well. It's just a lie fest. And yes, even Apple did this with this ugly ass pie chart, 3D pie chart. Shame on you. Shame on you, Steve Jobs, for that one. Sorry, may you rest in peace. This unjustified 3D, and there's a huge lie factor. They're okay with that lie factor, I'm sure, but I'm not. Here's the thing. I said no unjustified 3D. Turns out there are domains where you really want 3D. Spatial information should be 3D, right? If I'm doing a CAT scan of someone's brain, why not use 3D? Sometimes, why not use 3D? If I'm looking at airflow over an airplane wing, why not use 3D? If I'm looking at a heart arrhythmia, why not use 3D? You can justify it in that case because the data itself is 3D. Your sense making of the data itself, you're thinking about things in 3D. So looking at the data in there is 3D. Abstract data is not 3D. So don't make it 3D. Get it the hell out of 3D, please. I actually asked my students in my Excel class at Northeastern to make up the worst possible charts and graphs they could possibly do. I can show it to you if you really want. I normally show it to my Viz class. They really excelled. Oh my God, I threw up on my mouth a couple of times. It was deplorable. And it was all 3D with this huge perspective and a big ugly texture in the background. They were gorgeously ugly. I was amazed that you could actually do something that bad. Okay. And in case you think this is opinion, no, it's actually backed up with mountains of experimental quantitative data. It is well established. If you're making 3D, it better be 3D data. The actual data you're representing should be 3D as well. Michelle Borkin did a bunch of research, so including non-justified 3D. So one of the things that a lot of cardiologists look at would be, here is an artery, here is the blood flow through the artery, and they're trying to figure out where there's any kind of clotting, where people might have a heart attack. Okay, you might suffer a stroke. It's kind of an important domain. Well, all these cardiologists are using a rainbow color chart, which bad, and they're also using 3D. And Michelle's line was, well, why? You want to know where an infarction will occur, right? You want to know where these problem points are. You really don't care the shape of that artery. So why not put it in a line? And we'll do one further when we look at color. Why use that rainbow color scheme? Why not just use like a different color scheme that allows you to find things and have the critical important things like a very small dimension part of the artery really pop out. Have only the things that are critical pop when it comes to color. If you do not need the 3D, and it is 3D, you can get rid of it as well. Okay. In terms of accuracy, by the way, there's a strong effect of dimensionality on accuracy to the fact that how many disease regions were found, 39% in here and 62% in here. Now, I know you may not care that much, but I don't want to die because a person was looking at a 3D chart of my arteries. I'd rather them find the disease regions in my arteries. So maybe people's lives are at stake based off of how the data is being represented. That might be a good reason to not use 3D. So, in summary, to achieve graphical excellence according to Tufte, number one, above else, show the darn data. Right? He didn't say darn, but show the data. I agree with him on that particular point. That is the point, right? You're trying to maximize the data to ink ratio. I'm a bit less I guess, zealous about this. I'm not like, if you have any junk at all, it's wrong. But I think there is something to be said about not putting extra crap for no reason. Erase non-data ink. Anything that is not needed, he thinks get rid of it. I think if you leave it in, you better know why you're leaving it in. And you want to erase redundant data ink, which, again, we said redundancy actually might be useful. That's the last time in the visualization, in the perception and cognition lectures. So I don't always agree with him on this one either, but he comes from a time of graphic design. So where things are not changing or moving around, there's no interactivity. And therefore, if the image you get is the only image you get, you don't get like a different perspective on it. These are absolutely great things to follow up on. If it's interactive, you can get some other things out of your visualization. And number 5 is to revise and edit. You're not right the first time. Don't pretend you are. So when we do Dear Data, the postcards that we're going to be doing, don't expect the first draft of that postcard to be the right draft. Doodle some stuff up for a while. Expect some things that you can improve on, and then do another draft. Okay, so we're going to get rid of this as an unclassed activity. I think I have more than enough. But if you wanted, what would you do for an in-class activity? What would you do to clean this up based on the Tufte approach? So don't do this in in-class activity, but what would you do for a Tufte approach to minimize all of the extra stuff? Well, first of all, I get rid of the lines. You don't really need them. I get rid of the blue because it's not really needed. I might get rid of the outline. I might implied lines, Gestalt principles. You imply a line based off of based on that. I'd get rid of those little dashes, right? So the word percentage, and yeah, that'll probably do it. I don't think there's even percentage. You'll want a proper label as well. The thing about chart junk, like this, is that we already talked about that it's more memorable. So although it's clearly distorting the data, look, the axis is even being curved, not just height. This is the same chart, by the way, for that monstrous cost, but it is more memorable than the other approach. And so a little bit of pizzazz can be useful. And we talked about the fact that there are some papers that have shown that useful chart junk helps with memory and recognition. I still remember this graph, despite the fact I don't remember what the graph says. I remember it's a woman's leg, and I'm more likely to try and find that thing again later. And sometimes pictograms are actually quite useful. So here would be an example. Tufte even doesn't crap on this one. This from his 2006 book, Beautiful Evidence. And even he goes, yeah, sometimes you want to actually have images of the creatures you're putting in there. Why? Because you're more likely to remember. This is brain mass by body mass. So the larger you are and the smarter you are, like the amount of brain mass should, if every animal is equally quote unquote intelligent, you'd have a perfectly correlated line all the way up. So the larger the animal, the more brain mass they have, because as the animal gets bigger, the larger the brain. Notice the anomalous creatures: monkeys and dolphins and us, if you don't consider us monkeys. And on the other side, dinosaurs, not so smart. Fish, not so smart, or at least that kind of fish, not so smart. Ravens, quite smart. Goldfish, not so much. Okay. Now, you could have done it this way and put names on it. You could have done dots and that. You could have done all those things. But this is far more effective, having the images of the various creatures, far more effective in terms of appeal, but also just conveying the information. Not all visual embellishments are chart junk. This would be a glyph using, I think, each of those. So each of the petals of these flowers indicate a different dimension. And so you can actually compare across different countries and the different dimensions they're looking at. So, for example, what is the UK really, really good at? We're really good at work-life balance safety. right here. That's where the UK is really kicking butt. The US is fantastic at whatever this thing is, and that is your income. Well, I'm not surprised. Right? Their education, though, is not one of the best things. Sweden is far better at education in terms of this, in terms of the GDP of these G10 countries. What's Canada good with, right? Work-life balance. Work-life balance is the purple. This is safety. So we're pretty good at safety. What is environment? Surprisingly, because I don't think we're that good at the environment. Civic engagement we're better at. Education we're pretty good at. So these, Tufte might call that chart junk, but it conveys a lot of the information, and by putting it into a flower format, you are making it memorable as well, without hurting the data necessarily. Oh, and the actual height is how much is another essentially a bar chart as well. For chart junk can persuade, help with memory, engage. They can also bias, reduce reduce your data ink ratio, clutter, degrade trust. It really depends on the audience, the task, and the context. So you have to be conscious when you're designing something if you're putting chart junk in there. Okay, we're going to talk about small multiples soon, but I'll take a little break and grab a glass of water, and we'll come back to small multiples and design considerations for that. All right.